Okay, this is lecture 13 for delay. So now let's go to the review of our previous lecture. Yes, so in the previous lecture we have studied a way to estimate the delay of a complex circuit, and please have a look at this homework problem number 4. So I remember that we have already discussed this one. So when we consider the propagation delay of this V2 node, then what we can do is like this. Here we have a node and it has capacitance C, and we can just consider 2 times R, which is the resistance, effective resistance from this voltage source to our node, times its capacitance C is added. However, this is not the only one for our calculation. We have also another, although that is not connected to our output node, but that is also added to our path. In this case, we have to call this one as times C. That was our previous lesson. We have studied in the previous lecture. But there was another thing we have to keep in mind. In the previous lecture, there was a question about what happens if we working with this V1 node. So at the time, I told you a long thing. So if we consider V1 as a output node, then obviously R times C will be the constant related with this V1 node. However, at the time, I told you that that's it for this delay calculation, and neglect this C attached to this part, but that was wrong. So if you consider this circuit, then anyhow we have to consider the C contribution, the effort to fill out this second capacitor. Point is, the path should be a little bit carefully calculated. So although from this voltage source, this V2 node, we have 2 times RC. However, this is not the case for our resistance calculation. So instead of that, please, since this is the node, this is the output node, we have to find out the subset, so intersection between these two passes. Which pass? One pass is pass from voltage source to our output node, and another pass is the pass from our voltage source to our node of interest. So usually that is called as a lead. So when we make the intersection between them, actually we can find only the one corresponding to this one. So only this R should be considered in this calculation. So as I already posted in our lecture system, that time constant should be not RC but 2 times RC. So then if we adopt this thing, then I wanted to correct my previous lecture content. So let's consider this kind of thing. So that was originated from our NAND example, and this is once again voltage source, and this is now charged. This Y capacitor is Y node is charged. Then previously, when we consider this one, the time constant of this Y node, then I told you that actually this is the time constant, neglecting 3C and 3C, but it's not. So we have to also consider 3C and 3C contribution. However, once again, since this is output node and this is leaf node, we have to find the intersection between these two passes. What is the intersection? So in this case, this is the intersection. How about this? This Y and one node. Even in this case, only R is corresponding to the shared path, so we must multiply RC and RC. So that's the reason why we have this kind of time constant. So instead of that, now I wanted to ask you one more question. Instead of that, if we are working with the charging of an anode node, then what will happen? If we have this anode node as an output node, then our calculation should be R times 9 plus 5HC corresponding to this root, and we must consider the sum of R and 1/3 R times 3C, and we must consider also this sum, so 5/3 R times 3C. That will be the time constant for our N1 node. Okay, so now I have corrected my previous lecture contents already. So now let's go to the solution of our homework number 4. So okay, so although here I write down my previous convention, but that is V2 and this is V1 of our example. So our homework problem. So we are now considering V2 and V1 and its time constant. So what is time constant and what is time constant? The analytic answer is so the approximation is quite clear. For this V2 node, we have 3 times RC, and this V1 node, we have 2 times RC. And here you can see that we have 2 dashed line. This dashed line is corresponding to the exponential minus 3 times RC over T. And this blue line, blue dashed line, is corresponding to exponential minus 2 times RC. And what is this solid line? You can see two solid lines here and there, here and there. These solid lines are obtained from the accurate solution. So please make a comparison between these two things for your V2 node, and please make a comparison between these two things for your V1 node. So you can find that although it's not perfectly matched to each other, so clearly you can see that two red curves are not identical. Also, two blue curves are not identical. However, although that is not perfectly matched, but that is more or less looks similar. So, for example, if we just consider transition time, so propagation time from 0 to 1, then that will be the transition point, and you know that this is the error obtained from our approximation. Also, this will be the error obtained from our approximation. So finally, I wanted to finally correct my previous lecture. So what happens if I just use the things like the exponential minus t over rc? That is completely long, and in that case you will have this one. This is the one obtained from our long calculation for delay constant, and you can see that that is quite much off from our accurate calculation. Okay, so that was the errata for my previous lecture, lecture 12. Okay, so do you have any question on our lecture content?
지금 IC는 구체적인 값을 뭘로 하시는 건가요?
So in this case, that is really normalized. So that is really normalized, and when I calculate it, I just use R equal to 1 and C equal to 1. So in terms of its correct unit, for example, ohm, farad, whatever. So because in this case, the actually important thing is not just R, not just C, but only the product between them is important. So
디퍼런셜 있는데 그것들을 라플라스 트랜스폼에서 하신 건가요?
no. In this case, actually, in this calculation, I just drawn using the numerical calculations.
라플라스 트랜스폼에서 풀어도 되는 거죠?
Obviously, yes. Actually, that was one way I recommended to you. So either Laplace transformation or some direct solution of your partial differential equation. Either way is quite much acceptable. So, do you have any further question? So, then if you don't have any question, then I will move to the next one. But please interrupt me whenever you have a question. And now let's go. So anyway, now let's come back to our previous lecture content here. So the propagation delay can be expressed by this one. So propagation delay can be expressed by this kind of thing, and maybe you remember, instead of the real time itself, we prefer to the normalized one. So normalized delay is the time normalized by 3 times RC. But why that is 3 times RC? That is the time delay of a unit inverter. The simplest circuit we can imagine, or simplistic gate we can imagine. So in this case, what will happen to our delay, normalized delay? So if we delete or if we take this division, then you can find that D equal to just 5 over 3H. So that is the observation. One is there is a constant which does not depend on H, and there is a term which is linearly dependent on H. So what was H? H was fan out. So fan out just to describe how many dependent nodes are attached to our driver. So if H is large, then we have more and more dependent logic gate, for example. And so please wait. So pencil is just okay. So if we have fan out of 4, for example, then it means that we have the same copies of this. This is the case we can sync the fan out. So from this observation, now it is clear that delay, our normalized delay, can be decomposed into two terms. So one term is its own delay, which it does not depend on fan out. So even when we have unloaded gate, for example, if this is unloaded, there is nothing attached to this one. However, even in this case, when we make this transition, then it takes some time to have our inverted signal in the output. So although we start from t equal to 0 at this sudden transition, but actually we will have certain amount of time which is corresponding to 3 times RC when we consider unloaded inverter. It means that if we add more load here, another load here, then that will be postponed, and we have to wait for more time to have the transition. So simply speaking, parasitic delay is its own delay even when we have nothing related with this loaded gate. However, this effort delay is the effort to charge or discharge our dependent loads. So this is related with our load gauge. So what will be the linear term for our H, and what will be the constant term for our H? So you can easily understand this is constant term, and this term is the term linearly related with our H. Then now let's say that D equal to a constant plus then a coefficient and H. What is the coefficient in front of this H? That is our question. So before moving to the next slide, but let me just lead our slide. So delay component, we can find two things. This is just a repetition of my previous explanation. The first one is parasitic delay. It is the time for a gate, our driver, to drive its own internal diffusion capacitance. So please remember that when we consider this unloaded, our unloaded transistor, then there will be RC model corresponding to, if we consider discharging, then there will be something like this 3CR. Are you with me? Because this was the thing related with our MOSFETs effective resistance, and this 3C comes from the diffusion cap of our MOSFET and PMOSFET. So if you remember correctly, this 3C can be once again decomposed into two terms, C and 2 times C. And what was the origin of this C? That was from our N MOSFET, and 2 times C came from our P MOSFET. We assume that 2-to-1 ratio between our P MOSFET and N MOSFET to match our mobility mismatch. Okay, so that was the parasitic delay, and this type of calculation is done even without any load which is loaded the output of our driver. However, if we add more capacitor to here, here if we introduce more capacitor parallelly to this node, then that will give us additional time delay, and that is called as effort delay. This effort delay depends on the ratio of external load capacitance to input capacitance. Okay? This is fair now. So now let's go to the next section, 4.4. But before moving to this 4.4, I just wanted to show you the last slide for this RC delay model. Up to now, we have done the simple estimation of R and C out of our simple logic gate. So actually, at the end of our previous lecture, lecture 12, a student came to me and gave me a good question like this. So please think about this case. Here we have pull down network of our 3 input NAND gate. And what was our estimation for R at the time? So if we have certain number, then please note that at the time we just say that okay, there is a certain capacitance times 3C and 3C, and also there we have 3C component out of this 3 times wide, 3 times wide, and 3 times wide NMOS transistor. His question was like this. Here we have 3C. If we just remember the cross section of our MOSFET, then it is easy to say that okay, here we have C, diffusion capacitance, and if we make this width of our transistor 3 times wide, for example 6 lambda, in this case the value will be 3 times of our unit capacitance. And please note that this is the border between one transistor and another transistor. So if we have another transistor here sharing this node, then each of them will contribute 3C, 3C. So since they are in parallel, then if we think naively, then we can estimate that okay, there will be 6 times C originated from our 2 transistors. So are you with me? So it is one question by our student. However, the answer is no. Practically, the answer is still 3C. Please have a look at this one, this figure 4.17. Here you can see that red line corresponding to one transistor, and here you have another transistor, and here you have another transistor. There are 3 transistors, and in between you can find a green area. So you can clearly see this green area that is corresponding to the source of this transistor and drain of this transistor. Simply means that the blue dot shown here. So it's not drawn in this way. Here we have a transistor, another transistor, so it's a gate, and its gate and shared by certain metal, shared by another metal. This is not the case. If we have this kind of connection, between transistor, for example, transistor B and C, then of course this will contribute 3 times C, and this will contribute also 3 times C. However, in reality, if you go to the real layout of this transistor, actually they are merged into just one. So instead of this kind of redundant implementation, they just introduce longer diffusion layer and just to introduce another gate. So now this is a gate and this is a gate. In between we have a certain position. This is corresponding to drain of this transistor and source of this transistor. So they are just contributing just 3C, not 6C. Okay, so that was question. Okay, so depending on the layout, actually we can find different capacitances. So simply speaking, a good layout minimize the diffusion area. Why? Because if we spend quite a large area for diffusion layer, then that is corresponding to increase of our internal capacitance, then that is related with the reduction of the peak operation point frequency of our transistor. Okay, so now let's go to the section 4.4 for linear delay model. So this is quite a short one, this section. This is nothing but the observation like this one. Okay, delay can be decomposed into two terms. Two terms is the one which is related with its own diffusion capacitance. This is parasitic delay, and there is another one which is dependent on the fan out. Okay, so it's own delay even without any load, and the term related with the number of load gates attached to its output. So that's it. So delay can be decomposed into two terms. One is parasitic delay, and another one is that is called as effort delay. So what is the meaning of this effort? And this effort is the effort spent by our driver. Driver should pay some effort to charge and discharge the connected load gate. So that is called as effort. And as I told you before, here we have linear dependence on H, and here we have a coefficient, and this coefficient is actually a property of the driver. Okay, so now here let's have a look at these two simple examples. One example inverter, and another example is 2 input NAND, not 3 input NAND. So let me just consider this one. If we have just unloaded inverter, then what will happen? So if we draw its discharging phase, then you can see that there is 3C and R. Then you can see that the delay, related delay, will be 3 times RC. Since we are normalizing our propagation delay with this 3 times RC, so D will be 1 in terms of its parasitic delay. Okay, so then now say if we add the identical one inverter as its load gate, then what will happen? In this case, we must consider another one corresponding to 3C. So are you with me? Because if we consider if we consider this unit inverter, then it has also 3C as an input gate, because please note that when we consider this type of unit inverter, then it has the width of 2 and it has the width of 1, so it contributes 2C and it contributes to 1C. So that's the reason why we have to have 3C as input capacitor of our load inverter. So then if we count only the contribution from this additional 3C, then what will be the time constant? Since resistance is still R and this is 3 times C, then additionally we will have 3 times RC. And obviously, instead of this single inverter, let's say that we have 2 copies of inverter, then that is corresponding to yet another 3C. So we just add one more copy of 3 times RC. Simply speaking, if we have H times of load gates, then that will be just H. Say that if we have 4 dependent load gates, then what will happen? Our overall time constant will be 15 RC, and in its normalized form D, we will call it as just 5. Okay? This 5 can be considered as 1 plus just H, when H equal to 4. So are you all with me? Okay, so please.
프로포게이션 딜레이 타임인데 TPD랑
Yeah.
타우랑 서로 다른 개념.
No, so here I just omitted the propagation delay. So actually, please, actually when we say the propagation delay, then of course it can have 2 different things, like propagation delay for output falling or propagation for output rising. And when we say that this one, simply we just make the average between these 2 components. But accurate calculation of this tau PD will be very difficult. So instead of accurately calculate this tau PD, we just introduce a single time constant approximation. So for example, if we have, so let's come back to our previous example. If we have this kind of system and if we wanted to know the propagation delay from our X node to Y node, then in order to accurately calculate this tau PD, then we must run our SPICE simulation and measure the transition points. Then we will find out the accurate tau PD. However, instead of that, in this course, we will just use single time approximation, sometimes called as Elmore delay, following the name of inventor. So instead of that, we will say that, okay, tau will be 3 times RC. So let's say that is this 3 times RC is the real PD propagation delay corresponding to this definition? Actually not. We have to have a little bit more coefficient, and also our R is not very accurate. C is not very accurate, so therefore please regard this tau we are calculating as an approximation of exact tau PD. But still, as much as in this course is involved, then I would like to say, although this tau we are considering is not exactly equal to tau PD, but we will consider this tau will be a good approximation for our tau PD. Okay, so please. So the difference between these two components can be easily understood. For example, even when we consider the most simple, so let me just go to this way to have some space to write down. So even when we consider the simplest circuit RC, so the exact answer would be like RC times T. So it is like this, starting from, for example, normalized constant 1, then it will take some time to diminish. And actually, we are defining our tau p to the time cross the transition point, for example, half point 5. So then what will be the exact tau p? Tau pd. So if we spend the time tau pd, then it should be just half. Okay, so are you with me? Then we can just take the natural logarithm to left hand side and right hand side. Then eventually we will have log 2, and that will be minus tau pd over rc. Of course, this is just cancelled out. Then you can see that exact tau pd corresponding to our definition to cross this transition point will be actually having certain coefficient and RC. However, what is our tau single time constant approximation? We just say that, okay, if we have a RC circuit, then this is RC. So even in this simplistic case, our calculated RC and the real propagation delay will be different. However, that is not that much different, because this is close to 1, more or less they are in the same order. And you know that this case we have the exact solution. However, if we go to more and more complicated system, the accurate calculation of this tau PD becomes increasingly difficult. So that's the reason why the spice simulation will be the only way, circuit simulation will be the only way to predict this kind of transition or delay problem accurately. So now the remaining thing is only approximation or quick and efficient way to estimate it. So in this case, our approach is not that bad. Okay, so please understand this thing. So what was your original question? So I understood your question as the how much its tau is accurately following the exact value of tau PD. My answer is, even in the simplest RC circuit, it's not exactly equal to tau PD. And for realistic case, that can be more differed from our exact tau PD. But it's not that important, because the accurate value can be eventually calculated by circuit simulation. And as a designer, our goal is which topology seems to be more beneficial to have a short delay. So therefore, as a quick remedy for that problem, that difficult problem, we just take this kind of approach. Okay, so if you have any question, then please interrupt me more. But for a while, let me just go to this one. So now you understand this tau is not that exact, but you know that is a good approximation for our program. So now you can see that when we consider normalized D in this inverter case, it can be written as 1 plus H. It means that we have a leading coefficient of H, and this is corresponding to, once again, parasitic delay, and this term is corresponding to effort delay, and here we have one term and another term, H and coefficient, and they are also decomposed into two terms, like, you know, H is called as a fan out, and this one is called as logical effort. So this is effort, and effort is obtained by a product between logical effort and fan out. Okay. So now let's go to this way. If you are looking at this inverter sign, then D is equal to 1 plus 1 times H. It is easy to understand this D, but now let's go to more relevant example of two input NAND. So if we have two input NAND and one lab. First of all, let's try to draw our two input NAND here. So of course, so sorry, so pencil is not working properly for a while, so let's wait. Okay, good. Now in this two input NAND, how does it look like? So it has, of course, have P MOSFET, and there is P MOSFET, and we here we have bubble, and N MOSFET, N MOSFET. What will be the size of a P MOSFET to match our DC purpose? So at least we, in order to the effective resistance of R, then we have to have number 2 as a width of our P MOSFET, because you know we are assuming that P MOSFET is twice less powerful than N MOSFET, so we must have 2. Also, we must have 2 to match our P MOSFET, because when both of our P MOSFETs are turned on, then actually our effective resistance will be just half R. However, this is best case for our charging phase. The worst case will be only one of them is turned on and the other one is turned on. Therefore, we must have the P MOSFET whose individual effective resistance is equal to R. That's the reason why we have number 2. Then how about our N MOSFET, the pull down network? In this case, the only case where its resistance is important is this one is turned on and this one is also turned on. Then we wanted to have resistance of R.
추가라고요? 두 개니까요. 엠모스핏 두 개가 연결돼 있으니까.
Okay, so I mean that the overall resistance should be 2 times R. Yes. So in order to have overall resistance of these two serially connected N MOSFET, then each of them should have half R and half R. In this case, the sum of these two serial to have R will give us R. Okay, so are you agree? So in order to have half R, then our N MOSFET should be also sized with 2 times wider than unit transistor and unit transistor. That is the way of our sizing problem. So please remember our previous discussion on 3 input case. How was our 3 input case? So in the case of 3 input case, even in this case, our PMOSFET had a width of number 2 because our worst case was just one of our transistor was turned on. So yes, that was 222. However, in the case of 3 input NAND, then the case is overall we have to have a resistance of 3. So overall, and we must have 3 R over 3 for each transistor. So each MOSFET was sized with 3 times unit width. So previously it was 3, 3, 3. However, now this is 2, 2, 2. Okay, so are you with me? Okay, then let's just delete our blue colored ones, which is drawn for our 3 input NAND gate.
혹시 그 사이징 할 때 전류의 입장에서 생각을 해도 되나요? 이제 그냥 기본적인 인버터 1대2로 제작을 만든다고 했을 때 그게 그냥 전류가 흐른다라고 봤을 때 트윈드 랜드 같은 경우에는 피모스가 2개 있으니까 그 전류가 2배가 되고 그게 엠모스에 흘러야 되니까 엠모스의 사이즈를 2배 시켜야 돼요.
Please note that so you are so let me restate your question in order to share between our students. So his question, so in my understanding, his question is when we consider the sizing of these two pull up network and pull down network, how about considering the continuity of current flowing through this pull up network and this pull down network? So his question is understood this way to me. However, first of all, we have to understand this type of CMOS transistor never allows the direct current conduction between this VDD node and ground node. So therefore, there is no chance to have direct conduction between them. So in some cases, so I mean that depending on the combination of our input variable A, B, so we can have 0, 0, 1, 0, either of 1 is 1 or 1, 1 case. So in every case among 4 cases, so we have either PDN is on and PUN is on. So first of all, considering the continuity seems to be irrelevant in this case. But another one is what I wanted to say is here when you consider this case, only this part is the case relevant to our pull down network. Pull down network is only relevant when all of them are turned on, and in these cases these are all related with our pull up network. So therefore, in order to say R, effective R, it is quite obvious. However, pull up network, so we are more or less focused on this one. This one, what is this one? Only one of them is turned on and one of them, actually this is turned on and this is turned off, and we are considering the worst case in terms of power or strength of our pull up network. So why? Because we are considering the worst case. So worst case, if we say that, if we focused on this one, then what will happen? Then if we have this condition, then our pull up network will be too weak to drive our our diffusion capacitors. So that's the reason why we wanted to, even the worst case, the weakest case, we wanted to have the minimum uh, so not that high resistance given by R. So so I'm not quite sure my answer is fit to your question, but if you have further question, please come to me and I will try to answer your question as much as possible. So anyway, let's say that, let's assume that this is the typical uh, sizing of your transistors. Then now let's try to uh, find out the first parasitic delay, and after that logical effort. So are you with me? So in order to parasitic delay, first of all we have to find out the capacitor connected to this load. Then how large it will be. So in this case we have, yes, here we have 2C, and also that will give us 2C, and that will give us, here we have also 2C, there will be 6C. Okay. Okay. Then in this case we have already made some consideration to match our resistance even in its worst case to R. So we will have the configuration like 6C is driven by resistance of R. Then the tau will be 6 times RC. However, the normalization is done by what? Normalization is done by our unit inverters tau, which is given by 3 times RC. So D, which is originate from its own diffusion capacitance, will be just number 2. Simply speaking, when we make a comparison between our two input NAND gate and our inverter, actually the driver, uh, actually the effective resistance is the same as R. However, in the case of inverter, that was 3C, and now the capacitance becomes 6C. So 2 times large capacitances are attached to our output node. That's the reason why we have twice slower transition for our two input NAND gate. Okay, so you can also think about this one. So now let's go to this one. So now we have logical effort. So logical effort means that, okay, we have parasitic one, but also we have the leading coefficient in front of our H. So important observation is that is actually the thing related with the type of our logic gate. For example, what is it? This is inverter. And what is it? This is our two input NAND. And usually we are considering NAND in this case. However, what is it? So you can see that only when A equal to 1 and A equal to, either A equal to 1 or B equal to 1 can give us number 0. So Y, A, B, then 1, 0, 0, 1, 1, 1. In every case, we will have just number 0. What is it? This is nothing but our NOR. But when you have a look at this NOR, sizing seems to be a little bit different. So previously we had 2, 2, 2, 2, seems to be more balanced, but now we have quite wide implementation for our PMOSFET. So please have a look at this PMOSFET. In this case, we have to have anyhow once again R. So each of them should have 2 times half of R. However, when our PMOSFET has 2 times the unit width, it has just number like R. So in order to have half of R, then our sizing should be 4 times of unit width. So that's the reason why we have this quite wide PMOSFET in this pull-up network. Instead of that, in the case of this pull-down network, we can say just R, because this one will contribute a resistance R and resistance R. In the worst case, when only one of them is turned on, then overall resistance will be R. And in the best case, when both of them are turned on, then overall resistance of our pull-down network will be half of R. So exactly same as before in our 2-input NAND gate. So now you can understand there is a difference in sizing for 2-input NAND and 2-input NOR. So you can expect that also there will be some differences. So what is the differences? No, in both cases our sizing was done to have the effective resistance in the worst case is R. Then point is, when you consider logical effort, then the remaining thing is how large its input capacitance. So please have a look at this A node. From the A node, you can see that one N MOSFET and one P MOSFET. This transistor contribute to C. Also this P MOSFET will contribute to C. So overall, it will have 4C as its input capacitance. But please have a look at this NOR gate. In this case, you can see that 4C out of your P MOSFET and what else? Additional 1C from your N MOSFET. So simply speaking, when we have NOR gate, then its input capacitance will be 5 times C. Since its effective resistance is always R, so we will say that the logical effort is related with this 4 times RC, and in this case 5 times RC. Of course, we must normalize it to 3 RC, so we say that its logical effort is 5 over 3, and in this case we have the logical effort corresponding to 4 over 3. Okay, so are you with me? So So if you don't understand this concept, then please let me know. I can repeat this concept once again.
지금 C2라고 써 있는 거는 3, 4, 5 이렇게 써 있는데 여기 위에 설명하시는 거 뭐 30, 40, 50.
Yes, so this is 4, 5 is corresponding to this 4 and 5 input capacitance of your gate. Yes.
논리의 데폴트라는 게 그러니까 결국에 그 게이트 캐패시턴스를 충전하는데 충방전하는데 걸리는 시간에 관련된 것들을.
Yes, you're right. Here, let me just repeat once again. Conceptually, here we have a certain logic gate called as driver, and logical effort means that here we have a load. A load is here, and this load, from the viewpoint of our driver, it can be regarded as just a capacitor. And this capacitor is corresponding to input capacitance of the load. Yes, so this capacitor comes from this load. And how about the resistance? The resistance comes from that of driver. Okay. So this is the driver's resistance. Driver's resistance try to charge and discharge the capacitor of our load gate. This is the situation. And the logical effort simply state that when we have the same type of driver and load, then what will happen to this calculation or this time constant calculation. So please continue your question if you cannot understand my explanation. I can try to explain once again.
여기서 아래 해당하는 거는 여기서 어디가 아래에 해당하는 거죠?
No. So yes, that is a really good question. So the condition we are considering is not considering just a single copy of our 2-input NAND. So good question. The situation we are considering right now is not like this. We are considering the case. This is the input of our load gate, and here we have another NAND gate. This is 2 input NAND gate, and our R should be evaluated from this guy, not from this guy. So where can you find R in this load gate? It's not. If we have another load of this first load, then we can consider the resistance to drive this second load. However, in this current condition, this should be regarded as a load gate, and we have to consider the existence of another external driver gate, and its effective resistance is important for this kind of calculation. Okay, so good question. But please note that in this kind of calculation, we always assume that same type of logic gate. I mean that this G, this logical effort, is considered when a 2-input NAND is driven by 2-input NAND, and in this case, we are considering the 2-input NOR is driven by 2-input NOR.
그래서 노어가 가장 느린 건가요? G가 가장 크니까.
Yes, you are right. So if we have the same type of, let's say that, that is a really good question. So currently we have two different nodes. So say that what we can say is, okay, here we have a certain signal X and certain signal Y, and let's say that there is one thing. Currently we are considering the propagation delay between X and Y. How long does it take to send our signal from X node to Y node? So now we can consider similar case with NOR gate. Yes. So in this case, what we can say is, yes, let's say that we have the same amount of additional node, and the thing written by this logical gate is when you add additional dependent load to this Y node, then what you can expect is from this logical report is now your H value is increased by amount of number 1, and fan out is also increased by amount of number 1, and you can expect the increase of your propagation delay will be larger for your N MOSFET. And oh, sorry, not N MOSFET, so sorry about that. Your NOR gate, then your NAND gate. That is the thing you can expect. Then, of course, you can ask me the question like this. Okay, this is just incremental value of our delay. Then what happens if we don't have any of these loads? Then what is its own delay? Then that is related with parasitic delay. So please make a comparison with these two input NAND and two input NOR. Then you can see that in this case they are the same. So simply speaking, when you have just unloaded NAND and unloaded NOR, then you can expect a similar scale of propagation delay. But when you add one single NAND NOR and one single NOR, then what will happen? Then you can expect that, wow, now you have longer propagation delay for your two circuits. Okay.
So parasitic이 이제 낸드랑 로어에서 똑같다고 하셨는데,
Yes.
그러니까 그러면 여기서 낸드에서는 어떻게 되는 건가요? 그러니까 낸드에서 3C, 3IC, 그러니까 어떤 원리에서 똑같은지 좀 그러니까 낸드에서랑 로어에서 parasitic capacitance 똑같다고.
Okay. So it's like you can always come to, so please instead of newly explaining everything from the scratch. So now let's go to this case. So this is more complicated, obtained from more complicated case like 3 input NAND gate. So previously you have considered the situation like charging, and here we have, yes, so we, in order to calculate this kind of thing, so propagation delay, first of all we have to understand propagation. In the case of propagation delay, we must to find out the worst case. So when you have two input NAND case, you have four different cases, then please consider these four cases. And when you make this RC network, then you can try to find out this tau value. Okay, so I wanted to ask you, please do your own exercise for estimating this two input NAND and two input NOR. Okay, so due to time limitation, so now let's go to this table, the logical approach and parasitic delay. They share the same property. What is the property? I mean that in this case, when you have a certain input, number of input and gate type, then this logical approach and parasitic delay are given. So simply speaking, this kind of values does not depend on your fan out. Regardless of the fan out, these two quantities are property of your logic gate. Once you have, for example, two input NAND, then whether you have wider or smaller scaling for your NAND, then this value will be the same. Okay? So now let's go to our okay, we have only 2 more minutes, but let's try to cover our example 4.10. Now let's say that we have 4 inverters attached to here. So now we have 4 inverters and we will have 1 plus 4 because this 1 comes from its parasitic delay and 4 comes from our fan out. And you know, logical effort of this inverter is normalized to 1, so that's the reason why we have the delay of 5. Of course, please note that this delay is normalized to 3 times RC. So, for example, if we have 3 picosecond as 3 times RC, then actually our total delay will be 15 picosecond. Of course, please note that it does not necessarily mean that our propagation delay is exactly equal to 15 picosecond, but we wanted to have good approximation for this value. Another example, 4.11 is related with ring oscillator. Ring oscillator, for example, say simplest case. Let's say we have only 3 input and happen to be at initial time we have a logical number 1. Let's say, then after certain time, then what will happen? This will be 0. Then after certain time, then what will happen? There will be 1. Also, another certain time, then what will happen? That will be 0. Then what is it? This 0 is just connected to the metal line, so input over our this inverter chain is now changed to 1. Then after some time later, we will have number 1 and we will have a number 0. After that, we will have a number 1. So starting from number 1, after some time later, we have once again 1. It means that, please have a look at it. So starting from when we just measure our input value, input voltage as a function of the time, then when t equals 0, let's say that this becomes 1. Then how long does it take to be changed to number 0, logical 0. It takes 1, 2, 3. 3 times of unit transition is required. Okay, 3 times unit transition. After that, also 3 times of unit transition will be required to once again goes up to logical value 1. So 3 times unit transition. Then how long does it take from here to there? This unit transition is nothing but our d equal to 2. Previously, example 4.10, we have shown that this is when h equals 4, d equal to 5. However, now in this case, what is your fan out h? In this case, you have just one single dependent load and single. So h equal to 1, so your d equal to 2. So simply speaking, it takes 6d for your half period and 6d for your another half period. So overall, in order to have this transition from low or high to low and low to high, this can be regarded as one single period. So the period can be written as 12 times d. And this 12 times d can be, of course, well considered as 4 times d multiplied by the number of your stage, number of inverters n. So that will be the one period for your ring oscillator. So simply speaking, instead of this number 3, if you have 5, then you will have a longer transition time. So simply speaking, if you take the inverse of this period, this is corresponding to operation or oscillating frequency of your ring oscillator. So it will be just 4dn, one over 4dn. So you can see that. Oh, sorry about that. I just omitted this. That will be the answer for example 4.10. Oh, sorry about that. So we have already spent 4 more minutes. So sorry about this delayed end. But anyway, this is the end of our 4.4. Up to now, we have just considered a single stage, but in the last lecture, before our midterm examination, we will cover this 4.4. So we are quite close to the midterm examination. Then coverage will be up to this delay part. So please do your self-study, and if you have any question, then please come to me, or more preferably, please send me an email. Then I will answer your questions. And please come to our lecture room next Tuesday, because we have to have the midterm examination in this room from 9 o'clock. Okay. Okay, sure. So you will be distributed over this room, and we will have quite a simple examination. Okay, then do you have any further question? So since time is over, then now I want to wrap up today's lecture, and please come to me if you have any further question. Thank you.
마지막에 잘 못 들었는데
네.
수험이